All right, so at sort of the beginning half of that video, the guy on the screen whose name I forget, gave an explanation for the color of fireworks. Okay? And we're going to talk today about how burning things like metal salts and gases and looking at the colors that they produce allowed us to deduce something about the internal structure of atoms. Okay, so we're continuing again to talk about the electronic structure of the atom, and so we're first going to talk about this idea of energy levels. Okay, so at the very last class before the exam, we talked about the difference between discrete and continuous, right? Continuous is analogous to a ramp, and having discrete things are analogous to having steps and stairs that are only at certain heights. Okay? So we're going to talk about that in terms of amounts of energy within atoms. Okay? And so how do we know, okay, that electrons in atoms can only have certain amounts of energy associated with them, as opposed to electrons being able to have, any amount of energy whatsoever. Okay? And so this comes directly from experimental observations. Okay? So if you take a solid where the atoms are, closely packed together, and you may have different types of atoms there. Okay, what happens if you do what we call excite them, if you add energy to them, if you heat them, if you put electricity in them? So think of an old style incandescent light bulb, okay, where you have a wire, it's some kind of material, and you run electricity through it, and that causes that material to glow. Okay. That material is going to emit what we consider a continuous spectrum of light. So you see, something like a rainbow that's kind of a smeared rainbow where you don't see any specific lines of color. You just see kind of a smear of color, much like a rainbow in the sky. And so that is, an example of a whole bunch of different wavelengths, just, continuously varying and no gaps in between. Okay. Now, if you take atoms and you put them in the gaseous state, okay, so let's say we take some neon, okay, and we run electricity through that, okay, what we get is we only get specific wavelengths. We don't get this entire rainbow right here, okay? We only get specific colors of light being emitted. So before we talk about what that means and how we interpret that observation, let's just talk about what's the difference between a solid and a gas, okay? If we go back to our kind of middle school states of matter training, actually, my kids, one of the advantages of having kids when you teach science at the college level is you get to watch where different ideas are introduced in the curriculum. And so states of matter first appeared in my kids' education in second grade. So if we recall, right, in a solid, all of our particles are packed close together, okay? Whereas in a gas, okay, they are separate. And there's space between them. Okay? So when we talk about exciting our atoms, adding energy into them, and how they respond, okay, think about solids and gases differently. Okay, when you think about a gas, whatever you put in, whatever energy you put into that atom, okay, you're going to see what that isolated atom's response is to that energy. Okay? Whereas when you're looking at a close packed solid, okay, what you're going to see, okay, is what you would see. You're going to see the atoms' responses, but also how they interact with one another. Okay, so you get different information out of both. So imagine that you're somewhere that's super crowded. Okay, so I don't know, you're at some type of, let's say a concert venue that only has, standing room, doesn't have seats, and it's really packed, and there's a whole bunch of people, kind of shoulder to shoulder. And imagine if someone tries to push through the crowd, okay, right? They push that person, and it's going to jostle them, and they're going to bump into the person next to them, and they're going to bump into the person next to them. And the energy gets transferred between all the people, okay? So think of kind of that situation as similar to what would happen when we add energy to a solid, okay? So if we add energy to a solid, I may add, this atom may absorb it, but it's going to transfer some to the things that it's in close contact with, okay? So we're not seeing just how that single atom responds to the energy. We're seeing, both that and how it interacts with its neighbors. So if we want to understand the internal structure of single atoms, okay, we look at things in the gas phase, okay, in this type of experiment. And what we're going to see when we add energy, okay, is we're going to see how that single atom responds. Okay. So when we do that, okay, what we get is something like this. So I've got my hydrogen gas in a tube, okay, and I have, again, individual atoms here. And when they're in a gas, there's space between them. Okay? And when I run electricity through them, okay, I see light being emitted. Okay, so you can think of neon, the neon signs that you see. We have one in the physical science building. There's a science museum at on the first floor called the Science Discovery Center, and they have that kind of cool neon sign that has the kind of astronaut, and it says A.J. Reed Science Discovery Center. That is a typical neon sign where it's filled with gas, and we run electricity through it, and the gas glows and looks a particular color. Okay? If we then take the light that's emitted from hydrogen, okay, and we put it through a prism, okay, that's prisms, if you recall, separate out different wavelengths of light. So prisms are designed so that light of different wavelengths is going to travel through them differently. They'll have different kind of speed, they're going to come out at different angles based on, again, the wavelength of the light. So you can separate red from blue from yellow. And what we see with hydrogen is we see only specific wavelengths. Okay? And this is called a line spectrum. And I'm going to use our abbreviations here, lambda for wavelength. Okay? And when we do this for multiple different elements, okay, what we see, okay, is that different elements are going to give us different line spectra. Okay? And I used to, and a long time ago, when I taught this, I used to have like diffraction glasses that I'd pass out, and we had a device that had two different tubes of gases, and I, light them up, and you could see the different line spectra. Yeah. Different elements have different line spectra. Yep. So, and we used to do this demonstration in class, but I wounded myself one too many times on the device by forgetting that those tubes get hot, and also the device we had a short in it. So I, if I didn't remember my insulating gloves, I'd get burned and zapped with electricity. So now we just show you pictures. Yeah, no fun. All right, so these are all different elements, right? This is hydrogen. Okay. This is mercury, Hg. Okay, so you can, mercury gas, you can run electricity through, and neon. And so what you see, okay, is that different elements will emit light of different wavelengths. Okay? And the wavelengths are going to depend on the element. Okay? Now, what do we know about, just up to this point, what do we know about the differences between different elements? What makes hydrogen different from neon? The number of protons in the nucleus, right. And we're talking about neutral elements, so what does that mean in terms of electrons?
It's going to be the same amount as the protons.
Right, so if elements, in this case, pure neutral elements, differ by the number of protons, they're also going to differ by the number of electrons that are there, okay? So let's just look at hydrogen and neon, okay? Which one has more electrons if we're looking at the periodic table? So what's the atomic number of hydrogen? It's 1, right? Okay, so hydrogen has, a neutral hydrogen has, so I'm just going to remember neutral atoms here. So hydrogen has 1 electron. How about neon? What's the atomic number of neon? 10, right? So that means neon, neutral neon atoms will have 10 electrons. Yeah. Yep, and you can take your periodic tables out. We also have one on the wall here. All right, so what do we observe about the difference in the number of lines between hydrogen and neon? Yeah, Ben.
So on neon, there's more of the lines toward the center and the right. And with hydrogen, there's only one on the right. They're largely grouped over toward the smaller side of the rings.
Yep. So they differ in position of the lines. What's another difference? Yeah. The number of lines. Okay. So they differ. So elements will differ in the number of lines and their position, okay? And remember that each line represents a different color. This is just of the visible spectrum, okay? But again, we can detect wavelengths that with chemical instrumentation that our eyes can't see, okay? So we could presumably get line spectra that represent, the full electromagnetic spectrum. So different lines, different colors, different wavelengths. Remember that wavelength and frequency can be put in terms of the energy of those photons. Okay, so different color lines, different energies. Okay. So doing this experiment a lot of times on a lot of different elements, okay, led to, in the early 20th century, it led to a scientist named Niels Bohr proposing a modified version of the atom. So up to this point, we had a model of the atom where it was like, you got this small nucleus from Rutherford's experiment. We know the protons and the neutrons are in the small nucleus, and then mostly empty space, and electrons are somewhere out there. Okay. And so the development of what we call the quantum model, which is the modern model of the atom, the first step on that journey to the modern model was called the Bohr atom. Okay? And so the Bohr model of the hydrogen atom, okay, did a good job at explaining the line spectra of hydrogen. Okay? So when we're talking science and we're talking about the difference between like a hypothesis, a theory, a model, okay, when you do an experiment, okay, you take what you know beforehand, okay? So, when we did these line spectra experiments, okay, we had a notion that the electrons were somewhere in this vast region of space around the nucleus, but we didn't know any details, right? So we propose, based on, again, some observations, okay, when we see the line spectra, there's a proposal, okay, that, well, those lines are at specific wavelengths, okay, and the kind of interpretation of that data, okay, was that, then electrons can only exist with certain amounts of energy, certain quanta of energy, okay? And when we're interpreting our experimental data, okay, what we do is we develop a model, okay, to explain that data, okay? So the model, okay, will contain both a conceptual picture, which we're going to talk about on this slide, and, a mathematical representation of that conceptual picture. So the conceptual picture is kind of the picture in your mind of what's going on, and then the mathematical model is putting that in quantitative terms that can then be tested. So that mathematical model becomes your hypothesis. You do more experiments, okay, and you run the parameters that you're testing in your experiment. You put those into your mathematical model to predict what the outcome of your experiment would be, okay? And if the outcome of your physical experiments matches what the math predicts, you say, aha, my conceptual picture that's described by this mathematical model is correct, okay? So we're going to talk about the Bohr atom and a little bit about the math behind it, but we're not going to go into the math, okay? And we're going to eventually see why, this model was refined, if you will, okay, in further ways to get to our modern model of the atom, because it predicts some things very well and others not so well, okay? All right, so that's putting it, this into the context of, scientists doing experiments, right, and proposing models that, again, are our hypothesis for how things work, okay? And when we have enough data to support those, then we give them the kind of stamp of approval that we call theory, okay? All right, so what did Niels Bohr say a hydrogen atom looked like, or how were electrons arranged in a hydrogen atom? Okay, so his model, is shown on the right? So we already knew, thanks to Rutherford's experiments, right, that we've got protons and neutrons in the nucleus, okay, and that nucleus is a tiny fraction of the volume of the atom, where all of the mass is concentrated. Okay? All right, so what Bohr did is he came up with a picture of how electrons are arranged in that space. And what his model states, is that the electrons are arranged in such a way, as if they were in energy levels, orbiting or surrounding the nucleus, So you can think of this as if the nucleus were our sun and the electrons are different planets, orbiting the sun at different distances, So his explanation for why you get different lines with the different elements, is that different elements have their electrons different distances, from the nucleus, and those distances correspond to the electron having a certain amount of energy, So, imagine, if you will, is there anybody in here who doesn't have a driver's license? Okay, so we've got a few folks without driver's licenses. Have you been in a car that's going around a corner fast, though? Or a bus? Ugh. Hate going in buses when they go around corners fast. All right. So one of the things you may, have experience with, right? If you're driving in a vehicle, okay, you have to slow down when you're going around sharp corners, right? The speed of a car is equivalent to kinetic energy, right? The faster you're going, the more energy you have, the harder it is to control taking a sharp turn in a car, okay? So if you think about electrons having different amounts of energy, okay? And if you think of their orbits, those circles or spheres that they're traveling around the nucleus, the more energy you have, the bigger that orbit is going to have to be to kind of stay controlled, okay? So things that are farther away from the nucleus, okay, are those electrons that have more energy, okay? So farther away, we're going to call that higher energy, okay? And electrons that are closer, okay, are going to be our lower energy electrons, okay? All right, so Niels Bohr says, okay, the electrons are orbiting the nucleus and they have certain amounts of energy, okay? And we only see certain lines, so it must be like, the steps on our stairs. There's only certain energy levels that are allowed for each type of atom, okay? And the reason we see light, okay, is because when we put energy into an atom, okay, an electron can absorb that energy, and when it has more energy, it's going to go into a higher energy level. Okay, but eventually, it's going to relax and give off that energy and go back down to what we call the ground state. Okay, so he defined two states of the electron, the ground and the excited. Yeah.
So is that what happens in like glow sticks, for example, whenever you break them and they reach an excited state?
Yeah. So there's different ways of putting energy into atoms. Okay. I've talked about heat and electricity, right? So in glow sticks or in lightning bugs and things like that, the source of the energy that causes the electrons to move up and then relax back down and let off light, that is it's a chemical reaction, okay, that's transferring energy. So that's why like glow sticks don't get hot, right? They just glow. And that's called chemiluminescence. So we'll talk about fluorescence and phosphorescence and chemiluminescence. It's just the source of the energy in the glow stick or in the lightning bug is chemical rather than, a mechanical or heat kind of energy. So so moving between energy levels, okay, we've got the ground state. That's where we start. That's where the electrons like to be, okay? So the electron will always return here to the lowest energy state that it can, okay? And then the excited state is a temporary state where one or more electrons goes to a higher level energy state, a larger orbit region, if you will, okay, as a result of absorbing some energy, okay? So this is electron temporarily moves to higher energy level, and in the Bohr model, you can think an orbit. Now, our modern model of the atom, okay, in our modern model, the electrons don't go in these circular orbits. They have these other weird shapes, and, again, we're going to talk about why our experimental observations, okay, prove that that's not the case. okay? Because in an orbital model, right, in physics, okay, astronomy, we can predict where the Earth is going to be in its orbit 5 days from now, right? We know where we're going to be around the sun because we have this predictable path, okay? It turns out, spoiler alert, electrons don't have these predictable paths around the nucleus, okay? And that's the refinement that's going to happen on the Bohr model. But the Bohr model was the first one to explain line spectra in any particular way, okay? Now, the fact that there are only specific lines we see, okay, and only specific energy levels that electrons can be at, okay, is what we call the quantization of energy levels. Remember, so these are the steps that electrons can be at. And they are not always evenly spaced. So if we go back to our line spectra, are the lines you see in your line spectra the same distance apart? Always. No, they're not at regular intervals, okay? So different elements, okay, are going to have different size steps associated with where the electrons can be, okay? But they can only be at specific levels, okay? So that's what we call quantization. And those specific steps or specific levels, okay, we define those, okay, and we have a name that we give to each of these main levels, okay, that relate to the distance of the atom, okay, and we call it the principal quantum number, okay, and we give that the symbol lowercase n, okay. So the principal quantum number, okay, is going to tell you, okay, kind of on average how much an electron in an atom has. So the higher the principal quantum number, the farther the electron is from the nucleus and the more energy it has, okay? The higher the n, the more energy the electron has. And the farther that electron is on average, okay, from the nucleus. Okay. So hopefully you can see how this is going to relate to chemical reactivity eventually when we get there, right? There are going to be electrons that are the farthest from the nucleus, okay? And a couple things. One, they're going to have the most energy. Two, remember the thing that holds the electrons in the atom is the attraction that the protons, those positive charges, have in the nucleus for the negatively charged electron. The farther away you are, remember our Coulomb's law, how the distance was in the denominator, so the farther away those two charges got, the weaker the interaction between them. Okay, so this is going to help us explain chemical reactivity, okay, because we're going to have electrons that are less attached to their nucleus and more likely to interact with other atoms. Yeah?
So this is true even though this model is not?
Right. So we still keep actually the principal quantum number concept from the Bohr model. Okay? It's going to be the first of several different parameters that we use to describe an individual electron in an atom. Okay? And he is, and Bohr's model was right in that there are, certain primary energy levels, okay, that electrons are going to fall into. Where it was wrong is in the shape of how they go around the nucleus, okay? And so Bohr's model, okay, the mathematics of his model, okay, defined kind of orbits, circular orbits around the nucleus, okay? And experiments eventually showed that that was wrong, okay? So, in class, in our next class, we're going to be talking about how we're not going to be able to predict where an electron is. If we know it's here right now, we can't really predict where it's going to be, a millisecond from now, okay? And so that's where Bohr's model kind of breaks down. But let's talk about what he got right this time, okay? And talk about energy absorption and emission, right? So we said that there are energy levels that electrons can be in the atom. So why do we see those line spectra? Okay. All right, well, you'll notice again that our N's, okay, let me just change this so it's more visible. Our N numbers are always integers, okay? So N is always an integer. So we've got steps, 1, 2, 3, 4, 5, okay? And when we have our electron in our ground state, it's resting, okay? When we put energy into it, when we agitate it in some way, okay, that energy is going to cause it to jump up to a higher energy level called the excited state, okay? But it can't hold on to that energy forever, okay? And it's going to eventually release that energy and do what we call relax. So electron relaxes back down to the ground state, okay? So where do we get the line spectra? Why do we get light, different colors of light emitted? Okay. There are a number of different ways when our electron relaxes back down to the ground state and it gives off energy. Okay. There's a number of different ways that it can release that energy. Okay. It can release that energy, okay, as light. Okay. It can give back the photon it absorbed, and you'll see light of a particular color. And the light that gets emitted, okay, is going to have a wavelength and a frequency that's equivalent to the difference in the two energy levels. Okay. So why do we get hydrogen spectra that have, a blue line, a red line, and a yellow-green line? Okay, because the energy levels in the hydrogen atom are spaced those distances apart. Okay, so the amount of energy between, the ground and the first excited state, okay, corresponds to light of a wavelength that's, let's say, red. Okay, and if my electron absorbs more energy and goes up too, okay, the light that gets emitted, okay, is going to correspond to a higher energy photon because more energy was absorbed. Okay, so that higher energy photon is going to have a shorter wavelength and a higher frequency. Okay, so that's going to be more blue or green because those are higher energy photons. Okay, so emitting light, okay, so going directly from one energy level to another is one way that you can give off that energy to relax down to the ground state. Another way, okay, is that energy can be given off to the surroundings as heat, okay? Another way, okay, is we can have something called fluorescence, which we'll talk about a little bit later, where you have kind of a mixture of, giving off energy to your surroundings through motion, and then once you get to kind of an intermediate level, then giving off the light, okay? And that's what happens in things like glow sticks and, fluorescent highlighters, and things that glow under black light, okay? All right, so getting back to the model that Bohr defined, okay? So the model that Bohr defined, remember, our conceptual picture is this right here. We have electrons in orbits. The orbits are different distances from the nucleus. And when we move between them, we have to either absorb energy to get to a higher quantum number orbit, or we emit energy to get back to a lower quantum number orbit. Okay. Putting that in mathematical terms so that our picture in our heads of what's going on can make a prediction, and we can do an experiment to to test that. Sometimes I talk too fast for my own tongue even. All right, is shown up here. Okay, so this is when you do Bohr's mathematical model for the hydrogen atom. Okay, so the hydrogen atom is the one that we always start with because it's got the smallest number of particles in it, right? We got 1 electron, 1 proton, and so it's the simplest atom. The more protons and electrons you have, the more complicated the math gets, okay? So, so historically, we've always started with trying to explain the hydrogen atom because it's the simplest system. All right, so when you do that for the hydrogen atom, okay, you can figure out, okay, what those energy levels are for the hydrogen atom, okay? And basically, it's just a constant, okay? 2.18 times 10 to the minus 18th joules, okay? Remember, atoms are really, really tiny, and electrons are super, super tiny, have almost no mass, so you're not going to need a lot of energy to move them. And so this is a very small amount of energy, right? So this constant divided by the square of, remember that this is the principal quantum number, okay? Quantum number. So that gives us, okay, first of all, an idea of, again, how far you are, okay, from the nucleus is going to relate to your energy. Now let's talk about the sign of this energy, all right? Because I said that the bigger your N, the more energy you'd have, right? And if we just had 2.18 times 10 to the minus 18th divided by N squared, right? Your energy would, that number is going to get smaller the farther you are from the nucleus. And that would contradict what I told you before, okay? But we have a minus sign here, okay? So when the number gets smaller, okay, because there's that negative sign there, okay, the number itself getting smaller means the energy is getting higher, okay? So as N increases, okay, your energy gets larger, okay? Now, like humans, electrons like to be in the lowest energy state possible. They like to relax. They like to hang out at the lowest possible energy level, okay? So, lower energies in chemistry, if something has a lower energy value, okay, it is going to be a more favored state. We're going to talk about the thermodynamics of chemical reactions, and the more negative values you get from an energy perspective are going to be more favorable processes that happens, okay? So in chemistry, okay, lower energies are kind of more favorable, okay? So when your electron is near the nucleus, okay, that means it's going to be in a smaller N value, okay? So that principal quantum number is going to be lower or smaller, okay? That means your energy is going to be lower, okay? And lower energy is more stable. So the ground state for atoms, where the electron is at that lowest energy level, okay, is the most stable state, okay? So lower energy, more stable. All right, so we can take this equation, okay, and calculate for n equals 2, n equals 3, okay, and we can graph what those energy levels look like. So we like to draw things that we call energy level diagrams, okay, and those are the things that explain our line spectra, okay. So this is what's called an energy level diagram. So this is, although it may not look it, it's intuitive. The higher the line, the higher the energy, okay? So each horizontal line, okay, well that's, there we go. Your energy increases, okay? All right, so if you're looking at these numbers that are shown on the left here, okay, those are the potential energy levels for the hydrogen atom, okay? And what you'll notice, okay, is that we can correlate, okay, the position of the lines in the hydrogen line spectra, okay, with moving, okay, between different energy levels, okay? So this red line right here, okay, is when you have an electron, okay, that is starting at the n equals 2 level, and it moves to the n equals 3, and it relaxes back down. Actually, let me correct that, okay? Our electrons in hydrogen are always going to start at n equals 1, okay? So imagine that we excited it to n equals 3, okay? It can relax back down all the way to 1, okay? So if it relaxes back down all the way to 1, what we get is something that isn't in the visible range of the spectrum, really, okay? We get something in the UV right here, okay? If it stops, okay, at energy level 2, okay, which it can do, again, it can relax down to 2 and then relax down to 1, okay? Then what we get is we get our red line here, okay? And so when that one that has moved down to 2 then moves down to 1, we get another photon of light in the invisible to our eyes range, okay? So energy level diagrams, okay, for the hydrogen atom can be explained, okay, by the transitions between energy levels and by the Bohr model, okay? So, again, I just went over this on the previous slide, but you can make a thing move from, moving from energy level 3 to energy level 2. Again, that's where you get your red line, okay? All right, so we'll start next class, okay, by doing a few examples, okay? Yeah? So in order to go up an energy level, you have to absorb energy because you're going from low to high. To go from high to